Good afternoon, everyone. I start today's session by acknowledging the traditional custodians of the various lands on which we are meeting today. I recognise and pay respect to the first scientists and acknowledge the important contribution their unique wisdom provides to contemporary scientific conversations and collaborations. We pay our respects to their elders, past and present, and recognise their continuing connections to the lands, waters and their extended communities throughout southeast Queensland. It is my pleasure to welcome you to What on Earth is so good about Mars? A World Science Festival Brisbane 2022 conversation presented in partnership with Griffith University. Queensland Museum is proudly the exclusive host of the World Science Festival in the Asia Pacific and work closely with their presenting partners in New York to highlight the worldwide cutting-edge research and scientific discoveries. Now in its 7th year, World Science Festival Brisbane dares us to imagine what our future can be and how science can make it possible. Through the Griffith University and World Science Festival Brisbane partnership, together we embrace and foster access to STEM for residents of Queensland and for those beyond these borders. Mars represents an important step in the exploration of deep space. Over the last 5 decades, Mars has been visited by a number of satellites, landers and rovers. Together, this fleet changed our understanding about the evolution of our solar system and fueled the quest for life beyond Earth. Scientists around the world are learning more about Mars's atmosphere, surface and water content from rovers exploring and satellites orbiting the red planet. Today, we're going to hear what has been discovered so far, what this means for humanity, and how it's deeply important to remain curious and aspirational about deep space research. The moderator this evening is science journalist and broadcaster Jonathan Webb. As ABC's science editor, Jonathan manages a team of Australia's best science storytellers across radio, podcast and the web. Please enjoy the show, and over to Jonathan.
Hello and welcome. It might look like I'm on Mars and the weather is great, but in fact I'm on the beautiful country of the Turrbal and Yagara people in sunny Brisbane. I'd also like to acknowledge Australia's first scientists and offer a really warm welcome to any First Nations people joining us today. Now, if we wind the clock back to November 1971, Diamonds Are Forever, the James Bond movie, was about to hit cinemas, and Edwin Starr's War, What Is It Good For? Was a runaway hit. And NASA's spacecraft, Mariner 9, entered orbit around Mars. This was humanity's first lasting connection with another planet. And Mars 2, a Russian mission, got there just a fortnight later. In all of the years since, despite some big ups and downs, Mars exploration has become a global enterprise with decades of landings, crash landings, the first rovers, more landers and orbiters, more crash landings, more rovers, and 1 helicopter. We found signs of life, of water, tantalising hints of life, I should add, definite signs of water, and made increasingly ambitious plans for crewed missions to the Red Planet. We've also had 6 more James Bonds since Sean Connery, and we still haven't figured out what war is good for. Especially, perhaps, with everything that's happening on our little planet at the moment, the appeal of Mars and our fascination with the planet next door has never been greater. Europe, China, India, the US and the UAE all have active Mars missions. It's peak hour up there, and some of our panellists today are directly involved. But before we get to them, I want to ask you a question. When do you think the first person will set foot on Mars? By 2030? By 2050? By 2100? Or never? You can answer that question on screen in the chat. And while you're thinking about it, in about 1 minute, we'll meet the panel.
Roger, Mission Control. This is Mission Control to the launch vehicle. This is Houston
For today's discussion, we're joined by a terrific panel here in the studio. First of all, a researcher in the area of microsensing who has helped to produce and operate sensors used by NASA on not one but on 2 Mars rovers. Welcome Paulo de Souza, who appears thanks to our academic partners, Griffith University.
Thank you.
Hello, Paulo. Next is a member of the science team for the Mars Express ground penetrating sounder, MARS-SIS. She's a researcher studying impact cratering. It actually says in the script here, impact catering, but I don't think we're quite that far on Mars yet. There's no burgers. Impact cratering, also the volcanic and tectonic processes happening on Mars, and the search for ice and water. Welcome, Graziella. I knew I was going to muck up your name, Graziella. I'm really sorry. Graziella Caprarelli.
Hi, nice to be here. Thank you.
That was always going to happen. And finally, a man with a lifelong passion for space, and a co-founder of a space company that bears his name. Gilmour Space is one of Australia's leading rocket companies. Welcome, Adam Gilmour.
Thank you.
So, to start with, let's have a look at the results of our very quick poll. When do you think the first person will set foot on Mars? We have most people saying by 2050. So not too many optimists saying by 2030, just about 19%. 19% thinking we'll do it by the end of the century, and nobody saying never. So mostly fairly optimistic in the audience today. We'll come to what the panel thinks about crewed missions a little bit later. Firstly, I'd like to hear from each of you briefly your personal take on the subject we're exploring today, which is what on earth is so good about Mars? What excites you personally about our planetary neighbour? Paulo.
Well, I'm a Martian. I haven't told you yet. But yeah, Mars is a fascinating place. It is wonderful to see, of course, everything we have there, but gives us a key to understand how life was formed. And maybe that planet was also a place where life was present. But something happens in the evolution of that planet that differentiates us from Mars. Maybe our fate is to be like Mars, a desert that we have today, and we don't know. And the only way to know is to explore Mars. So that is why it's so fascinating.
The lessons for Earth on Mars.
And we have a DNA of explorers, so we have to go out and we have to explore.
Yeah, that's part of it, isn't it? Graziella?
Yeah, well, basically what Paulo just said. In addition to that, of course, Earth and Mars share a common formation history. When the solar system was formed, the planets, the so-called terrestrial planets, formed more or less by the same material. And so whilst on Earth, the record of that very ancient material is lost because of plate tectonics, on Mars is still on the surface to some extent. So it's very useful in terms of comparative planetology to study Mars because it can reveal also something about very ancient Earth.
Right, so the history is written on the surface because there's no tectonic plates sort of
that have subducted all the material and consumed
whatever. It's all
whatever.
sitting there for us to
Yeah,
to
pretty much.
Interesting. Adam?
I'm a little bit more basic. I love Mars because I think it looks a lot like Earth. It's not that far away from Earth. I mean, it is, but it isn't. We've already gotten there before. We know how to get there. It seems to have all the materials that we need to survive. And, you know, I'm a science fiction geek, so I think it's inevitable that we will live on Mars.
Bold. Yeah. And Paulo mentioned the explorer's DNA that maybe all of us carry a little bit of, some more than others. Also, in the introduction, the phrase was used that Mars is an important step in deep space exploration. And I found myself thinking, wow, what's the next? If Mars is only a step, where do you reckon humans might go after Mars? Is that something that we'd even think about?
I think we will. I mean, I'll jump in. I think the asteroid belt that's just outside of Mars is got so many materials in it. I think, you know, there'll be mining colonies there, and then there's a lot of moons of Jupiter and Saturn that look really interesting that I think we'll explore as well.
Paulo, you've been involved in working with rovers, though. Couldn't we get robots to do all the mining for us in the asteroid belt?
Yes, absolutely. And also some of those meteors passing by, or some of them we can eventually bring them down and explore that. Definitely, that's the future.
But does that need person power to be up there mining the passing asteroids? And
it's possible, but we could also have robots doing that, and probably we need to have them to start.
But I think there is a little bit more to that than just exploring for the purpose of resources. There is really the aspect of being humans. As you said before, we are explorers. We just want to go out there. And there may be different ways or different approaches to doing it. For example, obviously, at the moment, a human mission with humans, as we are, on a spacecraft will probably not go very far. But, I mean, I would be happy if we just went back to the moon, to be quite frank. But if we think in other terms, for example, a repository of DNA on a capsule that goes away in space, who knows where it can reach? And maybe if there are other civilizations that find these capsules with this DNA, they can reproduce a human there. It would be nice to have an idea of humans being elsewhere rather than on Earth and having fulfilled that explorer's mission.
Wow.
So keep thinking, because, you know, I think there is certainly scope to fulfill this ambition that certainly is innate in ourselves. And exploring Mars is just a step to that, because we test the technology to some extent.
We've just zoomed out a very long way and looked a long way into the future, which
Definitely.
was tantalizing. But let's start with what we've learned so far about Mars on the missions that we've sent. And you've been involved in some of those, Paulo. You helped design instruments for a couple of the NASA rovers. How much have those robotic explorations changed over the years?
Yeah, it of course, the first one, Mariner, that you mentioned, that was just a flyby, and then we got in orbit. And that was our first images that came from, was the first time we could see Mars so close by, because before that was just through telescopes. And we could see that there were some ice caps. We could see a little bit of the atmosphere. We could see the ice caps changing in size because of the seasons that we have on Mars. So that was interesting. But the first image was quite astonishing, because we could see that there were some valleys, there are some processes that could really be an indicator that water was present on the surface of Mars. But there was no direct evidence of that. And this is where then the mission called Viking landed with 2 landers.
Right.
And what we discovered back in the 70s was just primary minerals that would dissolve quickly if we have water present. So in a way, it's an indirect evidence that water was not present in those sites. And that was quite a big disappointment. And we forgot about Mars until we discovered a small meteorite that was found in Antarctica called Allen Hills. That was in 1984. So 84001 is the name of this meteorite discovered in Antarctica that has some structure that looks like bacteria, fossilized bacteria. We know the rock came from Mars because we can do like a DNA analysis of rocks by looking at radioisotopes. It was a mineral made of carbonate. Carbonate needs water to be formed. With fossilized, that looks like fossilized bacteria. That discovery was so important because it could be our first contact with extraterrestrial life. That was announced by the president in the White House at that time, was Bill Clinton. And he announced that we will go back again to Mars with a rover. And that's where then Sojourner was sent in 1997 and discovered the same thing, the same basalt. There was nothing there, just very primary minerals. What was wrong? Probably we landed on wrong spots. And then all NASA, ESA start sending orbiters to start looking at the surface and select places that we could land. The question for water was still present. And there is no place that you would find life that does not depend on water. So the water was the key for life. Want to find life, follow the water. That's the strategy that those space agencies have. And then we landed in 2004, right in January, with Spirit and Opportunity.
Yep.
These rovers that have big solar panels, and in those rovers they have the instrument that I helped build.
Yeah, right.
That does analysis of minerals containing iron on the surface of Mars. And at that time, with Spirit, we couldn't find much, but with Opportunity, we found then jarosite and hematite, 2 minerals that needs water to be formed. So Mars was wet. There were oceans in the past. The question is for how long those oceans were there. Was there enough to form life? Was enough to life to evolve into more complex ecosystems even? We don't know. And discoveries are still coming. Is there water present today on Mars and the SES on the ground? But is there life there? Are we alone in the universe? At the end of the day, that's what we want to answer.
They're big questions, aren't they? It's amazing to think that there could have been these huge oceans on Mars. I mean, it's dry on, largely dry on the surface at the moment. We can talk about ice later. But that means that robots like the ones you helped with can trundle around and explore. That was Opportunity and Spirit that you had instruments on. Where are they in this illustration?
Yeah, it's in the bottom side. So you have Opportunity and Spirit is just the same. They're twins, exactly the same. So you have Sojourner, that is there written NASA 1977, Opportunity and Spirit in 2004, and then Curiosity came 12. We landed then with Perseverance with the small craft, Ingenuity.
A little drone.
Yep. And then, of course, the Chinese that is still operating on the surface.
That's the one with the big solar panels on the left.
Absolutely.
Yeah, right.
Yeah.
So there's a lot that we can figure out down on the surface with those sorts of instruments. But Graziella, you've studied the planet from a little further away. From orbit. Can you give us a sense of the sorts of measurements you can make from that distance, which started, I guess, back with Mariner 9 in 1971?
Yeah, at the beginning, of course, you get images. Images are great because you get to see what's on the surface. Of course, we had telescope pictures, if you want, of Mars, and that started already, since 1800 something with Schiaparelli, who was an Italian astronomer, who was the first one that actually spoke about canali on Mars, which was then mistranslated in English into channels, leading someone to believe that there could be humans or human-made. But Schiaparelli, with his telescope, managed to give a very good impression of what was on the surface of Mars, and then obviously followed by the Atlas by Lowell. Who is the one that interpreted the canali as being perhaps human-made. And naturally, the closer you are, and orbiters get closer to the surface of Mars than you can do via telescopes, the more details you can find. So initially, of course, it's images, but then as the technology evolves, naturally you can put other sensors. You can collect data in the infrared spectrum. They can be very useful about knowing about the mineralogy on the surface, for example, the thermal characteristics, so the thermophysical characteristics. You can measure the power that a particular surface can reflect light, and that's diagnostic of the type of material, as well as absorb that light and then transmit it later as heat. That all these kinds of parameters are diagnostic of the type of material that you can have in terms also of the grain size, whether it's boulders, whether it's sand or fine dust. And in addition to that, then you have active sensors like the ones on the radar, for example, that I work with. And that's basically, it is the spacecraft itself, it is the instrument itself that sends a signal onto the surface. And in the case of the radar, the signal penetrates under the surface, gets reflected by some discontinuity, and then it gets reflected back to the spacecraft where the radar picks the signal, and then we analyze that signal. So there are active and passive instruments that you can use, but at the end of the day, it's all about acquiring physical characteristics, physical parameters, from which then we can extrapolate and understand and infer what's on the surface.
And that sort of ground-penetrating instrument is what you have operating at the moment on Mars Express, is that right? Which is currently one of quite a few things spinning around Mars today. What have you learned using those sorts of instruments about the history of Mars and how it got to be the way it is today?
Well, so first of all, when I first started working with Mars Express data, I was a member of the team for the high-resolution stereo camera. And for that, of course, it's about collecting images. And these were stereoscopic images, which means not only we got the picture of what's on the surface, but we could also have ideas about the elevation.
So that's like a stereoscopic, because
Yes.
means you've got the two images, so you can kind of get some depth.
Yeah, and you
on what you're
overlap
looking.
and you can see different angles so that you can calculate the elevations. So if there is a little mountain or if there is a valley, for example. And that was very useful because those elevation data are now complementing the MOLA, which is a NASA, long-standing instrument that has been collecting data about the elevation of Mars. So we can combine the data sets, which makes it a little bit more precise, not accurate, but a little bit more precise. So that was my first work with Mars Express missions. And in that sense, the high-resolution stereo camera was an advancement relative to the previous missions that were orbiting, because it provides large swaths of imaging as the craft revolves around the planet. And in this way, we were able to follow the geology around. So rather than taking highly detailed pictures of one tiny little outcrop, which geologically speaking is interesting but doesn't allow us to make a reconstruction, if we have the same resolution over a larger area, then we can operate like geologists think on Earth, which is you have a certain type of outcrop, and then you have to follow that outcrop to see where it goes. So that was a great advancement in that sense. And then, of course, all these image data are complemented by the other instruments that collect physical data. And the radar is one of them. So where we find a certain particular geological area of interest, then we can direct the radar to explore particularly that area. And then see what's in the subsurface. There is no geology in 2 dimensions, it has to be 3-dimensional. So with the radar, you can probe what's underneath and get a 3-dimensional picture to some extent. Of course, the radar has as its primary mission to look for ice and water in the subsurface. But in addition to that, as you are collecting data, you can also interpret them to figure out other information, which is more strictly geological.
Mm. And has this sort of work, building up, the picture of the surface and the picture of the deeper structures in the planet, has that given us any sense of the difference? So Paulo mentioned that Mars used to be a lot like Earth. It's not much like Earth at all at the moment. Mm-hmm. And there may be some lessons for us there. Do we know much about why, about where what led to that transition?
Yeah, Mars is much smaller than Earth. So because of its smaller gravity, it lost all of the molecules that normally would make up the atmosphere of Earth, which are very light and move very fast. They would have been lost. Initially, there was also a coronal mass ejection kind of episode that stripped the atmosphere of Mars completely, the early atmosphere.
So a solar flare effectively blew away
yeah,
some of
the
its
solar
atmosphere.
wind. I mean, essentially, it was all these ionized particles, and but eventually, after that initial episode, the gassing of the planet through volcanic activity led to a formation of a new atmosphere. By new, I mean 4 billion years old, more or less. And this, however, is very different than the Earth's atmosphere, because all the lighter molecules are lost to space because the gravity of Mars is too small to keep them trapped around it. So we have a very thin atmosphere, which is made mostly of CO2. Now, there is not enough atmosphere to have a greenhouse effect, which would be the only way where you can warm the planet enough so that whatever molecules of water are left can be liquid and can form oceans, rivers, etc. But there may be some transitional atmospheric astronomical situation where you can have a transient atmosphere building up for a few 100,000 years. And when that happens, it may be possible that this bigger atmosphere can actually warm up the surface in a way that liquid water could exist.
And those windows brief in geological time, those
Very
brief
brief,
windows could have been enough time for these oceans to develop to shape the rocks.
Well, there is obviously the northern hemisphere of Mars. It's a huge depression. So it's about 6 kilometers in some places deeper than the crust of the southern hemisphere. So it looks like if there was enough water to form an ocean, that's where the ocean would be. There are, however, some ideas that geomorphological information about coastlines could indicate that there was indeed an ocean, but these are not uniquely interpreted. So there are a bunch of possibilities there. Certainly, if there was accumulation of water, naturally you would find it in the deepest places of Mars, and that would be the northern hemisphere. So we still don't know in reality, but certainly there is water underground. It's not reachable in most places, but there should be water underground, and a lot of the water is trapped in minerals as well, as part of mineral compositions. As Paulo mentioned earlier, there are some minerals, jarosite, for example, they have water in their molecular structure. So there is water, may not be accessible.
There's a lot of talk about water, you know, whether it's there in small quantities and frozen on the surface, or whether it's underneath, the way you were just describing, Graziella. Adam, why is water such a big deal?
Well, I look at the technology first. So with water, you can use electrolysis and split it into oxygen and hydrogen. That's one of the highest performing rocket fuels you can have. So you can use that to get off the surface. You can also use the materials to work with carbon dioxide and make methane, which is kind of like what most people are thinking of now as they'll use for rocket fuel, and oxygen. You also need water to breathe, to live, oxygen in water to breathe. So, a lot of the studies on surface habitats on Mars rely on getting water from the surface to use for a variety of things.
If it's buried, how do we get at it when we're living on Mars?
Well, we're
using it for our rocket fuel and our drinking water and everything else.
We have to dig for it.
Right.
I've seen pictures, Paulo, you can correct me if I'm wrong, where diggers have just scraped the surface and seen some ice. So in some cases, it's just below the surface. And I've seen other maps of Mars that talk about patterns on the surface of Mars where there are bigger concentrations. And I think it's not as hard as it could be to find water on Mars.
That was an image from Phoenix, which is a replacement of Polar Lander that failed in landing. So they came back again. And that was a little trench on the surface just to look at the subsoil, the immediate subsoil. And there was a patch that evaporated a few hours later that there is no explanation by the temperature, unless there was some indication of water there. Mars is so cold that even the atmosphere at times get frozen. So the CO2 that is rich is 96% of the atmosphere. When it gets really cold, it forms the dry ice.
Dry ice on the surface.
Then very early in the morning, we saw a lot of pictures of that with Phoenix that evaporates back again. But that case that Adam made a reference to, it's not really CO2, it's water. So it's there in little patches, and that's something you have a direct evidence that, for example, instruments that are remote sensing like orbiters or satellites won't be able to detect. They can see things at scale. Rovers, you can navigate a little bit but see more detail. And looking at the literally sniffing rocks like a geologist in the field and do these little discoveries. So it's there, absolutely.
You've got to get there first, right? If we're going to live there and use the water to stay there and potentially to take off and get home again, we have to get there, and that's not easy. Adam, you mentioned that the transport was your thing. Take us through the steps on getting to Mars full stop. I mean, it might be a little different if you're trying to take people as opposed to a rover. But what are the steps and what makes it so challenging?
Well, you've got to escape Earth's gravity, and then you've got to do a boost that gets you into the orbit of Mars, and then you're not going at the exact speed of Mars, so you've got to do another boost to enter an orbit around Mars.
And that entering the orbit is quite challenging, right? I seem to remember that being quite a crunch time for some of the missions because, as Graziella mentioned, it's smaller, it doesn't have as much gravity as Earth, and you're travelling at a fair whack when you're heading past. So it's a bit of a handbrake turn to get into the orbit.
If you're cheating, so you can, and it's good to cheat. So you can actually do a rocket burn to slow yourself down into an orbit, but because Mars has an atmosphere, there's a concept called aerobraking, and that's basically where you kind of touch the outside of the atmosphere and it slows you down.
Right.
Some of the Mars missions, that have gone on lately, they haven't even aero braked so much as rammed straight into the atmosphere and used that to slow them down. And that takes a lot of energy away from the kind of propulsion equation. Right. And then you can land on the surface.
Because the less fuel you need for extra burns, the easier it is to get
there in the first place.
Yeah. Is that dicier as well, though, to just head straight forward and hope the atmosphere slows you down enough?
Very much.
Right.
Yeah.
But it's been successful.
Yep.
Yeah, I mean, it's pretty much the standard way of going to Mars now. It's like everybody wants to aerobrake because it just means that, instead of taking 1,000 kilograms to Mars, with aerobraking, you can probably take 2,000 kilograms to Mars. And, instead of landing 2 people on the surface, you can land 4 people on the surface. So a lot of materials have been designed to look at how to operate because the temperature goes to well above 1,000 degrees Celsius. As you're entering the atmosphere, you're going really, really fast. It's something like 30,000 kilometers an hour. So you go from that to slowing down to about 1,000 kilometers an hour in a couple of minutes, and you get very hot in the process.
Stressful couple of minutes. And it's a long way away, right? Like it's sort of hundreds, or depending on where the planets are, even 1,000 or more times the distance that like a moon mission would be away. And so by the time you hit the atmosphere, between that time and when you get to the surface, you can't get a signal to Earth and back, not even close, right? So things have to be able to drive themselves.
Yeah, Paulo was talking about it before.
Yeah, it's so far away that there's no way that you can get that. So everything is happening, and you know what happened 20 minutes before. And for that period of time, when you start seeing, okay, we are entering the atmosphere, actually, you're already on the surface, either in pieces or in a single piece. It depends. But yeah, the first way to reduce the speed is really going through that the friction with the atmosphere. You have a heat shield to protect the spacecraft, and when you are about 1,200 kilometers, you open a parachute. Even the atmosphere is just 1% of our atmosphere, still works. And then as you get down, most of them will have retrojets that will reduce further, very close to the surface. And then it depends. Some would be very complex in landing, like Curiosity or Perseverance with cranes and taking it away, or would be bouncing on the surface like was with Sojourner and with the Mars rovers. And then you have been bouncing on the surface until we stop, and then you open, and inside you have the rover.
The Sojourner bounced before it landed.
Yeah.
On its, like, I can't remember what Sojourner looked like in that illustration, but it didn't look particularly bouncy.
Yeah, it was the lander. There was a lander, and then it gets out of the lander. Sojourner doesn't have a camera in. What you have, the camera is in the lander.
Right.
So you can see a full photo of the rover from away. So then the lander you have, with the Mars rovers, you have the same. You have a lander. And inside the lander, you have the rover. The lander doesn't.
Then trundles out.
Yeah, but then there is no cameras on the lander for the Mars rovers. So you just go straight. Now you don't have landers with Curiosity and Perseverance.
They just get dropped on by these crane contraptions. Yeah. There's so much to get right, Paulo. I'm beginning to realise why people have crashed. Do you know what the success rate is for Mars missions that we're trying to land?
We have been better recently. My last experience was with the Phobos Grund, which was a Russian mission where we have an instrument on board, and it didn't even reach our orbit.
We missed the planet altogether.
Yeah, it exploded on the way. But sometimes it crashes there, like with Mars Express, with the lander that we call Beagle 2. So I have one instrument on board.
Yeah, that was the British one.
It's there, but it didn't communicate back to the spacecraft. So
eventually it was actually photographed by something else. I can't remember what instrument photographed it, but one of the latest missions orbiters actually found it. I said, there's Beagle over there.
Yeah. The Americans have the best track record,
of landing
on the surface of the moon, of Mars, and then everybody else is pretty patchy.
Right. Okay. And so you mentioned the Beagle 2. So you're working on the satellite. You have an instrument on the satellite, Graziella.
Yeah. No, I
and there was that went with a lander, which we never heard from. It got down, but we never heard from.
Yeah.
I mean, the lander was Beagle from Mars Express, which is where Mars is. There was another attempt at landing, I think, with a lander called Schiaparelli, that opened the parachute either too late or too early. I can't remember which. So there was some kind of software malfunction there, though. Otherwise, it would have landed.
Or maybe the Air Force on Mars did something else, but yeah. And the atmosphere changes a lot, so you may have a very compact atmosphere if it's too cold, and if it's too hot on the surface, you have the atmosphere going up. So it changes as well the height of and that impacts on how you're going to transmit the last parameters of the landing. We have to do that with Spirit. So we got news that the atmosphere looks a little bit too high, so we have to change the parameters of the landing to plan for that entry.
Do they test things out on Earth with prototypes before the stakes get a lot higher and they're trying to use a parachute on Mars?
There's a lot of simulations and things you can do. Of course, we test things like parachutes and all the airbags, but you can't simulate the same gravity. It's 38% of our gravity, so it's not really the same.
Yeah, I was going to ask,
may have a mass equivalent. Yeah,
Right.
So you make it lighter, so you can go, if Curiosity weighs about 1 ton here on Earth, and that would be 380 kilos. So it's pretty light. So the easiest way,
scale it back and test it, right?
Yeah. So you scale down the weight. So the shape is the same, the size, everything, but you just change that. And
So it's the same effect as dropping the gravity, and so you test it out there. But where do they test them? Where's the most Mars-like place on Earth and they can test these things?
It doesn't need to be exactly like that. You try to find places that is not too rocky. We were super lucky to land with Sojourner, to be honest, because there are so many big rocks there. So candidates for landing usually would be relatively flat, relatively simple in terms of terrain. You have to study that really well. We have today about 170 potential candidates for landing, and we just go picking one after the other based on specific science questions that we want to ask. So in which place might be the best one to answer that question, and that's how we go.
All these different missions originating in different parts of the world. Graziella, you're using data from a European mission at the moment, the Mars Express. How does all of this cooperation work as an Australian working on a European mission? It all sounds brilliantly global and cooperative, but I'm sure it's not always quite that straightforward.
Well, no, it actually is. And, I am European myself, so for me it was easy to access. I mean, all of my former university colleagues from Sapienza in Rome, they were all involved in missions. I picked up the phone, said, I would like to work with you guys, is that okay? and that was relatively easy. I also was at NASA for a couple of years on and off. In Houston, and that was on a NASA fellowship. So if you are a scientist, you have an idea that you would like to work and propose a project to either ESA or one of the co-investigators teams or principal investigator teams, and or submit a formal proposal to NASA, which is what I did when I went to Houston. If the project is good and I think you can actually do it, it's generally possible. But certainly none of the missions are carried out by one single nation, that's for sure. Because the knowledge that you require, and let's face it, once you send something which is so terribly expensive up to Mars, you want to cram in as many experiments as you can. Otherwise, you're wasting money and you're wasting an opportunity. So naturally, you try and make a call globally to all the scientists and all the groups that have the capability and that are interested in running experiments to produce instruments. So each one of the instruments that I use, for example, with regards to the data, are in fact collaborations between NASA, ESA, sometimes JAXA, the DLR, the Italian Space Agency. They are all a combination of expertise. So the teams are actually very, very large. Once you get the papers published in Science, you have hundreds of authors there for a very simple reason, that everyone needed to contribute a little bit. Because not one single nation or not one single agency has the whole expertise. So all of these missions are in fact collaborative. we talk about NASA mission or as a mission because that's the initiator of the funding spree, let's say. So you start searching for approval. One of the agency leads that process of approval. But at the end, it is really a collaborative effort. No one can do it alone. There are some countries, I mean, there has been clearly the Indian satellite a few years ago, which managed to put this satellite in orbit for $6 million, apparently. They did it all by themselves, as far as I understand. That was a demonstration of capability more than anything else. The Chinese are pretty much doing it alone as well. It's a huge country anyway. But even with the latest rover, the Chinese rover, for example, some of our team are also helping processing the data and analyzing the data because it's the science. So. Yep. And one brilliant thing that NASA does extremely well, ESA has tried to do it, but doesn't do, in my opinion, as well, is making all the data from the missions available to everyone. So they have their protocol, which is PDS protocol, in the way that the format of the data has to be produced, so that they go into an archive, which is easily searchable. Yep. They also have versions for educators and the public, and that actually every scientist has access to those. In fact, when I first started, I started looking at those data. So the data are out there. Whoever is curious and has the expertise can use those data and interpret them. And we, in fact, are looking for more and more people to help us sift through the data, because there is a lot of stuff there which has not yet been unearthed.
Yeah. So scientifically, being open and collaborative about what you found is almost as important as collaborating on getting there with,
for sure,
with the missions. And ESA, which you mentioned, that's the European Space Agency, sort of European version of the NASA, the Americans. Are there other agencies that are less open and transparent about the data they've collected? You mentioned China sometimes is going it alone in terms of some of their technology.
Well, I mean, it's too early days to know. Some of those missions are still too young to have produced data that can be then put into the public domain, kind of thing. So we don't know which way they're going to go. But certainly, if you want to maximize the output of your mission, that's when you have to make your data open to the world, so that more and more people work on the data and more information is extracted, rather than having it sitting down in an archive that nobody reads.
Many minds make light work. There is an important question to raise, I think, at the moment, though, which is that probably for the first time since the Cold War, the collaboration between Russia and the West in space is under more of a question mark than it has been. There was a Martian mission planned that was a collaboration between the European agency and Russia that was due to be launching relatively soon. Where do you think that's at, Paulo?
Yeah, that's ExoMars was, it's planned to be launched in September this year, and we can send things to Mars every time we want. It has to be close by each planet.
Because if Earth and Mars are both going around the sun, and you don't want to try and
every
reach
2
it west.
years. You have to wait 2 years before you can send something to Mars.
So if we don't send in September now, the next window will be in November 2024. And this is a collaborative mission where we have the Russians participating. I'm a close friend of the Russian principal investigator, Daniel Rodionov. And that is really, we don't know exactly what's going to happen. We have some accounts saying that it's very likely that this mission is going to be postponed. And that is because of the embargo that is going to hit Russia. Some colleagues in ESA said that we're still optimistic that that is going to happen. But it's not a time to be unsure about the launch. So at this time, we should have all the systems aligned, everything in place. And Adam, is fabricating rocks. So this is what he does, and you can't just do that in a heartbeat. It's a serious project. Either you do it right, or you just postpone it. That was what happens to that mission 2 years ago again. So it's a lot to happen. So it's very unlikely to go, and that is a consequence of the Ukraine impacting our and the Russians impacting our ability to learn more about the surface of Mars.
Do you think a decrease in cooperation, or I guess it's more, can you see a decrease in cooperation resulting from the political tensions and the war in Ukraine, Adam, in terms of the longer-term ambitions of sending rockets and people out to Mars? Can you see that this, if there does end up being a lack of cooperation, that might have an impact or a delay?
Well, I hope it doesn't, peacefully. I hope this is a short-term thing that we get over. The country that's actually got the biggest ambition for Mars outside of the United States is China. So I went to a space conference in Singapore a couple of years ago where somebody from the Chinese Space Agency did a presentation on all the vehicles they were doing, and they're working on a vehicle almost the size of the SpaceX Starship, and they're saying they definitely want to have a crewed mission to Mars in the 2030s. So I think, if you're looking at somebody with a lot of money, has the ambition to go, it's China. And, I hope that we can collaborate with China on some of those missions, the rest of the world.
Yep.
Yeah, and what's likely to happen, either you collaborate and you save budget, you share experience, you share capability, or you go into what would like a Cold War, and then you're going to have a race. It's one racing against the other. And to be honest, I think probably if I have to bet, I would bet on the China mission. The Chinese are likely to be the first man to walk on the surface of Mars.
There we go. You heard it here
I'm not sure I agree with that.
All right.
I think Elon Musk is going to have a real crack at it. SpaceX is really well funded. They're going to the moon. They're going to test the technology on the moon first. I think that they'll get to Mars in the early 2030s. I think that's the race, SpaceX versus China.
Interesting. I really want to get to the subject of crewed missions and the mechanics and who's going to get there first. I think that'd be a great place to finish. There's one question I'd like to see if we can explore a little bit before we get there, and that's before we put our dirty boots down. Is there life already there? It came up briefly before. You mentioned the fact that something that looked like it may have potentially been something a bit like a bacterium was found in a Martian meteorite in Antarctica, and there's water in the form of ice, possibly quite a lot of it, certainly below the surface, but very cold. Graziella, what do we know about that water and whether life could survive in certainly cold, possibly frozen water beneath the surface of Mars?
Well, okay, so what we actually found were very bright radar reflection that we interpreted as being liquid water because it's the only material that we know of, based on how the radar has been built, that can produce those reflections. So having said that, obviously we are looking at minus 70 degrees centigrade, so how can water be liquid in these conditions? Anybody's guess. Our best hypothesis is that this water contains lots of salt. So salt acts as an anti-freezing agent, and so that at least in patches this water can remain liquid for a reasonable amount of time. Now, we know that I'm not an astrobiologist, so I don't know about the possibility of life and how it would manifest itself, whether we would even be able to recognize life if it's not exactly like our own. But that's another philosophical story. But the thing is that where you have lots of salt in liquid water, then you have a dead capacity of the water to retain free oxygen. And so essentially it makes the water more breathable, if you want to speak in the sense. So it's possible that some type of microorganisms might actually live in those conditions. Hence, our discovery now a few years ago and a couple of years ago about the patches of liquid water on Mars may actually be an impetus for people who actually study exobiology to look at particular kind of hypersaline environments and the type of life that can develop in those environments. Certainly not work that I would be doing myself because I don't have that expertise, but it's nice to know that it might provide the impetus for other types of scientists to do that kind of research.
Paulo, if we do find evidence of Martian life, I don't want to say a Martian because it conjures up unrealistic images, I think. As you mentioned, it may well have been a bacterium. What do you think it might look like? And what would it mean to you if there was concrete evidence?
What it means to all of us, I think, where we came from, how life was formed on Earth. Was that just a wonderful coincidence? Was a touch of God? How life is formed, and that is a fascinating question that is still with us since we start thinking about ourselves and our place in the universe. And the closest place we can get to, it's just another planet nearby. But if you look at the dimension of course, the size of the universe and how many stars we have out there, and all these stars, some of them have planets around, and some planets with conditions like ours. Definitely there will be thousands and thousands of planets, but too far away for us to go to. We don't have the technology there. We need to have more other space technologies helping us to really advance the technology in terms of rockets. But this is what we can go, and that I think it will be a fascinating discovery, and it's really impactful if you think about that there is life somewhere else and how that life was formed and then eventually evolved, and how those ecosystems are potentially existing today, and probably the universe will be full of life elsewhere.
Yeah, it does. If, like you say, if there's plenty of life here, and then you go to the planet that just happens to be next door, and if that's also had life, then it kind of totally adjusts the odds for how much life there is out there, doesn't it, Paulo?
It does.
Or could it be a possibility, and Adam, I think this is something you've thought about, that life either started here and went there, or the other way around?
Oh, there's been studies. There's an Australian scientist, I forgot the name, could be Paul Davies, who thinks that life started on Mars and asteroids hit, brought the microorganisms to Earth and seeded the Earth. They've definitely done studies where they've found tiny microorganisms floating around on the space station on the outside for like 9 months, still alive.
That's these things called tardigrades or water bears, right? Like funny, down a microscope, they look like a funny little pig or something, but they're just, you can freeze them and they come back to life.
Yeah, that's not even like a single cell organism. That's like a thing that has legs and a mouth and stuff. So if they can survive for 9 months, there's some good evidence that bigger asteroid chunks or bits of the Earth or bits of Mars can hold microorganisms on there for the journey.
Even with entering an atmosphere and
absolutely,
getting hot.
If it's big enough, the centre will stay protected. So yeah, quite possible. That's why, like, even if we find life on Mars, I think the jury's still out on is it out there. We'll have to go even further to the moons of Jupiter and Saturn, where there should be life there as well.
Yeah.
That's a whole other session, right?
Yeah.
Enceladus.
We might have the answer quicker because of one of the rovers is collecting parts of little rocks, and very interesting, very good candidate samples. Perseverance is doing that and then leaving those capsules behind, that another rover will come, collect them, put inside the rocket and ship back to Earth. So we can collect those samples and analyze with instruments that we could not miniaturize. I can't miniaturize a cyclotron, large instrument, a particle accelerator, or a scan electron microscope. It's extremely difficult to miniaturize and to have it inside the rover. So I will be able then to see the samples with more powerful instruments that we have today. So these are just probing them, finding interesting rocks, putting them inside these capsules, and then bringing back, and maybe inside one of them we will find this micro.
So never mind sending humans to Mars, just get some Mars and bring it back to you and your X-rays.
Yeah, that's the real invasion, the Martians invading Earth. Yeah.
And the Perseverance rover is doing that, right? Collecting samples and bagging them up and leaving them there. What's the plan for getting them back again?
It's to land another rocket sometime next decade and just to bring them back.
Right.
Yeah.
What are the chances? Can I get a number maybe out of each of you for the chance that Mars held life? Adam?
I think it's like 90-something%. I think we're going to find life all through the solar system. It's just, like, if you look at Earth, it's everywhere. It's in the coldest environments, the hottest environments. It is just so spread out. I think we'll find it. We'll find it either in a cave or somewhere in one of your lakes, or in any of the moons that have massive oceans of water around Jupiter and Mars.
Yeah.
Saturn.
Paulo, where, like 90 feels at the high, it might be at the high end to me.
I'll put 10% more there. I would say 99%.
Wow.
Yeah, we do have evidences, indirect evidences of presence of water. We have that little trench that found a little deposit. We had oceans on Mars before. We have all the geological evidences of that, and that was there for millions of years. Either we had life before, I don't think there is a question, but it is really if there is life today, and I think there is. But this is a question, do we have or not? So we have to explore the planet and realize if we have or not.
Graziella, you want to put a figure on it?
Yeah, I'm a little bit more pessimistic in the sense that I would be delighted if we discovered, traces of microbial life naturally. That would be a discovery of the century, if not the millennium. But whether that's likely or not, I'm not so sure. Europa perhaps is a little bit more welcoming in that sense, and that's why we are sending missions to Europa, including a radar, an Italian radar again, to probe underneath the surface, which is icy, and see that there is liquid ocean underneath. And there may be life there. That would be my next port of call. With Mars, I'm a little bit more skeptical, simply because we do have quite a lot of meteorites now that we, even though the rovers are not returned samples back that we collected, but meteorites, we have a good record of Martian meteorites. And aside from those odd-looking concretions that may have looked like the traces of microbial activity, the evidence is not that there is none. On the other hand, we know even from meteorites like the Murchison meteorite, which was an Australian found one, that there are nitrogen-rich compounds. Usually nitrogen is associated to organic material, which eventually also leads to proteins and life. The chirality is different, so the orientation of the molecules is different than what you would expect on Earth. But what I'm saying is that organic material is common all over the solar system, but organic material per se does not make life. And so it's a little bit more complex than just going and saying, okay, we've got this nice example of a molecule that looks like it could form a protein. It doesn't happen that easily in that sense. Having said that, life is ubiquitous, for sure, in the universe. I'm not sure in the solar system, but certainly in the universe, I'm very confident. For that, I would give easily a 99.9%.
There you go. Okay, just not sure about in the...
Not in our immediate vicinity,
right.
No, I don't think so.
If we return to the idea of us heading that way, Adam, Tyson has asked in the chat, will the first people to go to Mars get to come back again, or is it going to be a one-way trip? I've definitely heard people suggest we might need some people to leave and expect never to come back if we want to, get some boots on the ground. What do you think?
I think they'll come back. The reason why there's some studies out there about leaving people on the surface is, if you put it in like orders of magnitude, you need a 3 times the size rocket leaving the Earth to get people back than just leaving them there. Because you've got to take things onto the surface and you've got to bring them back. But I think the current thinking is if you can generate your fuel on the surface of Mars, which everybody thinks you can, then getting back isn't that hard. So I think the first missions will be people will go down there and then they'll come back again. I think it'll be whoever does it first, it'll be magnificent for, if you think it was a big deal that people came back from the moon, I think people coming back from Mars with all of the kit that they'll bring, all of the samples that they'll bring, will be unbelievable.
There'll be a lot, like it was dicey with the moon. Each step is even riskier when it comes to Mars.
It's right? A lot riskier. I mean, it takes 3 days to get to the moon. It takes between 6 and 9 months to get to Mars. You've got to wait on the surface for the traditional mission for about another 18 months, and then you've got another 6 to 9 months to come back. Radiation is probably your biggest danger. There's a lot of radiation in space, a lot of radiation on the surface. You've got to take all the food, all the water. You've got to have things that are redundant. Very, very tricky, but not impossible.
Would you do it?
No, I don't want to. I want to go to the moon. I don't want to go to Mars. I don't want to be away from my family for 2.5 years. But the moon's, the moon's like a holiday destination. We can get there in 3 days, come back in another 3.
So you do the moon, but not Mars. The moon wasn't the question I asked, but interesting. Graziella, you can figure out a lot from orbit around Mars, but just imagine if you could, set foot there and pick up some of the dust and have a proper look at it. Would you be tempted?
Yeah, that's why I'm not a field geologist, but a geophysicist. So I know things remotely from a computer, but definitely you're going to need humans in order to inform the decisions of where to look next. And yes, artificial intelligence and the rovers can do quite a lot these days on their own in terms of also making decisions where to go and look. But at the end of the day, if you really want to learn more, you need to get some humans. Now, whether I think that the first humans will come back or not, well, I wish they did come back, but I'm not as optimistic as Adam is, unless we forbid missions, unless we know for sure that humans are going to come back. And that means that you are no longer maybe looking at the 2030 threshold, but far ahead beyond in time.
Paulo, would you like to set foot where we've put the wheels of the rovers?
In a heartbeat, I would go. Yeah, it's again, it's that exploration side. I have to walk there. I'm not sure if my life insurance will cover that. I have to figure out that, but otherwise I'm gone. Yeah, I would go in a heartbeat. It will be just more than samples and things we can bring. Is to bring the stories and the feeling that you have been on the surface and what you explored and how looks like the sky. Of course, we can see from and how looks like Earth from Mars. And we have photos taken from our rovers on the surface of Mars, looking at eclipse like Phobos going in front, one of the moons passing by in front of the sun. Or
it's a big horizon, right? Like some of the shots from the rovers, it's nothing between you and that red horizon.
Absolutely. And the sky would be just absolutely wonderful to be seen.
No light pollution.
Just to be there for one night, just to look at the sky and see Earth in the sky, I think that will be wonderful.
What a lovely note to finish on. Thanks, Paulo. I'd like to say thank you to our panel today. A wonderful discussion. Paulo de Souza, Graziella Caprarelli, and Adam Gilmour. Thank you very much. And this has been the last of the sessions from the online World Science Festival Brisbane 2022. So thank you for joining us, and we really, really hope to see you in person for the World Science Festival Brisbane 2023. Thanks very much.